lights up. You get these big low pressure centers that create a big pressure gradient or a big pressure difference between high and low. That low pressure gets in close proximity to a high pressure, which is farther south, and in between the two, it starts to blow.
These powerful storms generate an enormous amount of energy that gets transferred from the air to the ocean.
You have three things you need when you want big waves, and this is the best place to get them. You need wind speed, how fast it's blowing. You need fetch, which is the distance of water that the wind is blowing over, and then duration, how long the wind is blowing over that. So if you get a 60-mile-an-hour wind blowing for 4 days, over 2,000 miles of ocean, you get some pretty big waves.
The waves at Mavericks can get as big as a 4-story building. But no matter what the size is, all waves are measured by three things: the height, the period, meaning the time from crest to crest, and wavelength, or the distance between the two peaks.
A 20-second period will be 20 seconds between the height passing an area, and 20 seconds is actually a very long time, and these waves can go about 14, 15 miles an hour. So if you were to take 20 seconds, it's a huge area.
In deep water, even when the wind stops blowing, the amount of energy in the wave is fixed and conserved.
Now the energy travels, but the water itself does not. The water itself just is moving in a small circular motion. Sort of like if you play with a slinky. You know, you can take a slinky and flex it, and you can see that wave motion going up and down the slinky, but the actual metal or plastic part of the slinky is only moving a little bit.
If the wave energy below the surface reaches the bottom, the seafloor acts like a speed bump and the wave slows down. The same amount of energy then gets compressed as the wavelength decreases. The only place for that energy to go is up, and the wave height intensifies.
All of the energy for that wave will be stored between the surface and a depth that is about half the wavelength. When the ocean depth gets to about half of the wavelength, then that wave transforms into what we call a shallow water wave.
Okay, we watched a little bit of a video there on waves, and we'll tweak some of these ideas right now. So basically, first thing we want to say, what is a wave? Is a wave, and ultimately what they said, waves are caused by wind acting on the ocean. It's a matter of energy, pressure differences, and so on. A wave is a method of transferring energy. Okay, through some medium. And what do we mean when we say a medium? A medium is just some stuff. Okay, we just finished up our mechanics unit. Mechanics. And mechanics has to do with the study of kinematics. That was what I had taught you earlier this year. Kinematics, how things are moving, velocity, distance, time, acceleration, and so on. Mr. Forrest just finished up with the study of dynamics, and that's got to do with the forces that cause motion, momentum, and stuff like that, energy. Okay, you put those two together, and that's the study of mechanics. Moving things, moving objects, and so on, describing them, measuring them, and so on. Now we are looking at mechanical waves, ultimately, to start off with Physics 11 anyway, and then we'll take it into electromagnetic waves and so on. But first we want to take a look stuff we can feel, tangible stuff that we can look at and describe. We talk a lot about water waves, like we just watched in the video, because we've all seen them, and it's something we're fairly familiar with. We can relate to that. Okay. So first off, a wave is a way of transferring energy. Let's take a look at a few key things here in terms of types of waves, and then parts of waves. Okay, first we're looking at this type of a wave. This is a transverse wave. Key thing you notice here, you may notice, is the idea of this red dot that they've marked out in the water. It's making little circles, but ultimately it's not really moving anywhere. The wave starts over here and moves along. If you can follow my cursor, I know it doesn't show up very well, moves along and repeats this pattern. But the water ultimately, if this is a water wave, is going to just stay put. Okay, a wave of this sort, a wave where the medium is moving kind of up and down, relative to the medium or where the rest position is called a transverse wave. Okay, the particles move back and forth that way. The energy moves transverse to that, perpendicular to that. Okay, I'm going to give this a little push. Whoops. Do it with the mouse. Okay, and I can pause it. And what you see here is I've given a push sideways that way. That doesn't show up very well, but giving it a push this way. Let me just, can I get this running again? And you can see that the energy is moving to the right, and you've got these regions here where we call them a rarefaction and a compression. So that type of a wave is called a longitudinal wave or a compression wave. So a wave where, and that's not very good drawing, I'll get a little better picture of it here, where the energy moves that way and the particles also move back and forth that way, is a longitudinal wave, is the most common way. No wave, I don't think it's spelled that way. Here, and we've got a picture of the transverse wave, and this is the longitudinal wave down here. Now a couple of key parts. Okay, right here where the waves are close together is called a compression. We push the molecules, if you will, very close together. And over here where they're fairly far apart along that section there, they're more rarefied, they're less compressed. So that's a rarefaction. Okay. Good example of this type of a wave, this would be a sound wave, right? S-O-U-N-D. A speaker, right, often has a cone and it moves back and forth, and the air molecules in here, when this pushes them together, you get an area that would be a compression, and then when this speaker cone moves back, you get a rarefied area, and it just continuously moves back and forth there. Now a transverse wave, obviously we're thinking about a water wave. A couple of key areas here. Up top, we probably are familiar with the part of a wave called the crest. Down here at the bottom, like the feed and trough, that's the trough of the wave, T-R-O-U-G-H. Hard to see there. Okay, and a couple of other key things we're going to look at now. Okay, here's a transverse wave, and you see each time I click the go button here how this thing moves, right? Where my arrow started off on the top here and ended up on the top here of this arrow. This thing is moving like a wave would. Now this distance here to here, the top of a crest through a trough to the next crest, is what we would call the wavelength. This distance here would be the wavelength. Seems like a good name for it. One thing that's a little bit tricky, we don't use the symbol W for this. W in physics has something else. We use this Greek letter lambda to symbolize the wavelength. Could be measured in meters, could be in centimeters, and it doesn't have to be measured from the top of the crest to the top of the next crest. It could be measured from here at rest position through one complete trough, one complete crest. Over there, that would also be one wavelength, or trough to trough would also be a wavelength. Number of different places we can measure it. Okay, other key things to measure here. This distance above rest. This is the amplitude, the maximum distance that this thing is displaced, from rest, is the amplitude of the wave. Now amplitude could also be measured down here from rest position. This gray line here is the rest position. This would be the water when there's absolutely no energy added to it, whether it's something tapping the water or the wind, of course, like they said. So that's the amplitude there, or the amplitude there. The wavelength we've got, again, this was a crest and this was a trough down here. We already looked at a compression and a rarefaction. So So that's the key things that we want to talk about right now. Now, waves, as they travel along, I said in the video, they have speed. And speed, of course, is distance divided by time. Now, if the distance traveled is from, well, let's say from here to here, then it's gone one wavelength. So we could talk about the distance as being the wavelength, and of course the time to go from here to here is the period of a wave. Now, I'll remind you quickly from Physics 11 at the very beginning of the year, we had our ticker timers and we talked about frequency and period of our ticker timers. We measured them. I think our frequency was 60 hertz, meaning it tapped up and down 60 times. Frequency is the number of dots per second, or in this particular case, if you're watching the waves go by, it's going to be waves per second, if that's the best unit. I mean, it could be per minute or per hour as well if they're going really slow. Period just means period of time. How long does it take for one complete wave to go by? So it's seconds per dot. If it was our ticker timer, or here with waves, it's going to be seconds per wave. A couple of other little tweakings that we had here. Well, first, the symbols. Frequency is an italicized F. Period is a T for period of time. If it's dots per second, then the unit is hertz. Okay. Now you notice here that both the frequency formula, if you will, and I hate to call it a formula, it's really just a mathematical ratio. Okay, I hate memorizing formulas, but they are the reciprocal of one another, dots per second or seconds per dot. So we can express these things T equals 1 over F, or F equals 1 over T. Okay, the relationship between period and frequency. Now, putting that in right here, for T, gives us velocity is wavelength over, well, T is 1 over F, so I'll put 1 over F. And we don't like to write a fraction within a fraction, so when you divide by 1 over F, it's the same as multiplying by F, the reciprocal of that. So velocity is equal to frequency times wavelength. Well, I guess we got ourselves an equation here. Velocity is frequency times wavelength. This is called the universal wave equation. Okay, very important. It applies to water waves, it applies to sound waves, it's universal. It applies to electromagnetic waves, so we're going in this unit. Okay, so a couple of key things. We need to remember our idea of period and frequency for waves, our parts of the wave there we've looked at. Here's where we're going to go in this unit. We are going to look at number 1, reflection of waves. Okay, number 2, and that's not an unfamiliar word, I'm quite certain, for all of us. We are going to look at refraction of waves. That might be a new word for you, but that's where we're heading in the next day or two. 3, we're going to look at diffraction, all these words that end with I-O-N or T-I-O-N. Diffraction of waves. And finally, we'll get away from the T-I-O-N. We're going to look at interference of waves. And once we've looked at all of these for water waves in particular, maybe sound waves as well, we're going to carry on and specifically look at light as a wave. Is light a wave? They used to be doubted somewhat, so that's where we're heading.